Welcome back to The Explainer. Okay, today we are setting the stage for a critical look at the hidden bottleneck in AI's massive physical footprint. We all know that AI models are getting smarter, faster, and more capable by the minute. But behind that magical software is a very stark physical reality of steel, silicone, and a whole lot of electricity. Today, we're exploring a truly fascinating breakthrough from MIT called the Energizer Framework. It's a tool that is completely flipping the script on how we measure, manage, and ultimately tame the massive energy costs of data centers. So let's dive right in with a frankly staggering projection from the Lawrence Berkeley National Laboratory. According to their data, by the year 2028, U.S. data centers are on track to consume a massive 12% of the country's total electricity. 12%. To put that into perspective, that is up from about 4% today. Think about that for a second. We're talking about a single tech sector taking up more than a tenth of an entire nation's power grid in just a few short years. Part 1. The AI energy crisis. Data centers are quite literally colliding with the power grid. Because you see, the explosive growth of AI workloads isn't just some abstract trend happening in the cloud. It is rapidly devouring our physical power infrastructure. Just tracing the severity of this crisis over a few short years paints a pretty clear picture. Back in 2020, the launch of GPT-3 really brought the first mainstream awareness to the massive carbon footprint required to train these large models. By 2021, baseline U.S. data center power consumption was hovering around 2%. But then, 2023 happened. The generative AI boom, think models like ChatGPT and Stable Diffusion, caused a wild 300% power surge in hyperscale data centers. And now, here in 2026, MIT has published the Energizer Framework right as we stare down that 2028 projection of hitting 12%. And you can really see this escalation at the hardware level. Back in 2020, the standard NVIDIA A100 GPU ran at a 300-watt thermal design power. By 2026, the GB200 GPU jumped to an incredible 1,200 watts. That is a massive, massive leap in just a few hardware generations. We're talking about facilities that were initially designed for 200 watts per server rack, now suddenly trying to figure out how to handle 50 kilowatts per rack. It's wild. Which brings us to Section 2, the estimation bottleneck. Simply put, you can't optimize what takes days to measure. So you might be wondering, why can't we just easily fix this energy drain by building better energy budgets? Well, it comes down to a crippling measurement bottleneck. Traditional instruction-level simulation tools, the standard software used to predict energy use, can take up to an hour and a half just to estimate the power usage of a single isolated AI workload. And keep in mind, an hour and a half is just for one specific model running on one specific setup. Think about what this actually means in the real world. The old way of doing things requires hours of simulation, often relies on completely obsolete GPU architectures like Volta or Pascal, and sometimes it literally depends on having the physical hardware right in front of you to profile it. But the new way, what the industry is desperately crying out for right now, demands fast software layer predictions across dozens of configurations at once. When data center engineers need to test 50 different hardware setups, those hour-and-a-half increments multiply into days of agonizing waiting using legacy methods. It is just a complete roadblock to efficiency. But here is the absolute game changer. MIT's new tool slashes that wait time down to a mind-blowing 1.8 seconds. Yes, you heard that right. From an hour and a half down to less than 2 seconds. This isn't just some marginal incremental improvement, it is a complete paradigm shift in how quickly engineers can iterate, test, and forecast power consumption. Section 3. Enter MIT's Energizer I, the 1.8-second software solution. This is truly the David to our Goliath. Created by researchers at MIT and the MIT IBM Watson AI Lab, Energizer completely rewrites the benchmark. Older simulators like Excel Watch, they take hours. Even using NVIDIA's own NCU profiling tool takes 8.5 to 35 minutes per workload, and you literally have to own the physical hardware to run it. Energizer, on the other hand, takes 1.8 seconds. That makes it up to 3,856 times faster than NCU profiling, all while maintaining an incredibly low 7 to 8% error rate. Oh, and the best part? It works on modern chips like Ampere and Hopper without needing the physical hardware on hand. This lightning-fast estimation unlocks the intelligent use of something called DVFS, or Dynamic Voltage Frequency Scaling. Now, DVFS is a fundamental energy management technique that lowers the GPU's clock speed and voltage to save power when maximum performance just isn't needed. It works exactly like a dimmer switch for your living room lights. Instead of having the lights blaring at 100% all the time, you dim them when you don't need the brightness. Energizer basically allows operators to accurately predict the absolute perfect dimmer setting, saving power without killing the workload's throughput. Section 4. How Energizer works. Algorithms, not clock cycles. Let's break down the mechanics behind the magic here, just to understand how MIT bypasses those tedious hours of simulation. So instead of simulating every single microscopic electrical signal and clock cycle, Energizer uses 3 highly structured steps to model power consumption. It basically takes advantage of the fact that AI workloads use really predictable, structured software patterns. Step 1 is workload representation, where it extracts the tiling and pipelining patterns of the AI operators. Step 2 is the performance model, which builds a structural execution timeline. And finally, step 3 is the power model, which feeds that predicted module utilization right into a standard dynamic power equation. So it's calculating power based on the software's mathematical blueprint, not by running a massive physical simulation. And this lightning speed absolutely does not sacrifice quality. Look at these accuracy numbers. We're talking an 8.0% power error on the server-grade NVIDIA 8100 and 8.2% on the A10. But here's what's most impressive. It achieved just a 7.0% error rate when forecasting the power of the newer H100 Hopper GPUs. That's hardware that wasn't even in its original training set. And to top it all off, this entire end-to-end prediction is handled completely on a standard Intel CPU. You don't even need a GPU to predict how a GPU will behave. How cool is that? Moving on to Section 5. Real-world applications. Across the entire AI stack. So how does all this incredible science actually translate out of the lab and into the real world? Well, this quote from MIT provost and senior author Anantha P. Chandrakasan perfectly captures its widespread impact. He states that to really make an impact on sustainability, we need a tool that can provide a fast energy estimation solution across the stack for hardware designers, data center operators, and algorithm developers. This isn't just a niche tool for one specific type of engineer. It's a completely holistic solution. Ultimately, this empowers decision makers at literally every single level to test, design, and forecast without burning through precious time and money. Data center operators can now compare 50 different resource configurations in a minute and a half instead of waiting 50 hours. AI algorithm developers can finally check a model's energy footprint before it goes live, totally avoiding those massive, unexpected electricity bills. And hardware architects, they can explore the power implications of completely new GPU designs before they ever spend millions fabricating the actual silicon. To put a very real dollar amount on this efficiency, for a hyperscale data center running thousands of GPUs, achieving just a 5% power reduction by intelligently applying that DVFS dimmer switch using Energizer's predictions, well, that translates to an incredible $4.4 million saved annually. That is a massive, massive financial incentive for these companies to get power estimation right. Finally, Section 6, a sustainable AI future. Visibility drives behavior change. Let's look at how this software acts as a truly vital, proactive tool for climate sustainability. As lead researcher Kyungmi Lee emphasizes, once you give developers the ability to actually see their energy costs upfront, in real time, they will naturally start making more efficient design choices. Think about it. If an AI developer sees that tweaking an algorithm slightly saves massive amounts of megawatt hours without hurting performance, they're obviously going to do it. Visibility naturally drives better behavior. And that leaves us with a pretty fascinating thought. As AI continues its relentless scaling, will the existence of lightning-fast, accurate tools like Energizer drive new industry regulations? Could we actually see a future where pre-deployment energy disclosure becomes mandatory for all major AI models before they're allowed to launch? I'll leave you to ponder that massive potential shift in the industry. Thank you so much for joining this explainer. I really hope you found this deep dive as fascinating as I did, and we will catch you next time.